Hey, well, thanks for joining in today on another fun FE Civil review, and this is a Tuesday, right? Get it? Tuesday. It's 2/22. It's a Tuesday, and this is just fun. And if that was a bad joke, don't worry. It just gets worse, and you don't even have to stay for the end. But if you want to stay for the end, I got a good one. It's a concrete joke, which actually is kind of fun today because today we get to talk about two of my favorites. Too. I'll try to keep the puns limited, but the fun thing is we get to talk about steel and concrete design. So the way that this works here is structural engineering is a knowledge section on the FE exam, and what we're going to do is we're going to take a look at specifically structural design. So last time what we did is we looked at structural analysis. So if you've missed that section, you can definitely go find it. But this time what we're going to do is look at structural engineering and specifically design. So steel, concrete design, load combinations. This is F, G, and H. And I wanted to go over these specifically in a separate section because they're two of my favorites. But you know, it's all good. So if you have questions, put them in the comments. I'll try to respond to them as we go. There's a little bit of a lag, so if I don't hit it right away, I'll do my best to respond. But also just one other thing here, I started adding a QR code up above. So if you print these off and are trying to get back to the stream or the channel, you should be able to use that QR code to get back to these videos as well. So hopefully that helps somebody, maybe like two of you out there, but who knows? If things like that are good, you can give a like, but whatever. We'll just keep going here. So we're gonna jump in. And the way that I did these problems is I made them so that, I don't know if they're more complicated than maybe what's going to be on the FE, but I tried to take a look at like one or two problems that'll kind of really capture the essence of what I think is fundamental in these topics. So we're going to just jump in here and take a look at question one. So we're going to work through this again, just with questions, answers, and hopefully get some, get this to work. But, for those of you taking the FE, definitely wish you the best. So here we go. Question one, a portion of a building is shown below. The direction of the span is as indicated. So span directions, if you're not familiar with steel design, span directions, they typically go one way. So this means the load is kind of going to get distributed kind of horizontally here. So the direction of the span is indicated. This is a typical symbol you would see on a steel framing plan as well. So if you haven't taken a steel design course, you might not know that, right? But it's like kind of thinking like if you were to lay planks down here and just lay a whole bunch of planks across, that's kind of what the deck is doing. It's spanning from like one beam to the other. So we'll take those out, and what we have is the structure must support a dead load of 85 pounds per square foot, and a live load of 125 pounds per square foot. So these are the loads that are given, and using LRFD load combinations, typically LRFD is I think what's going to be used. Maybe if you've already taken the test, you can let me know if ASD is used, but typically I go with LRFD because concrete's pretty much primarily LRFD. In practice, some people do ASD for steel design, but I'm going to stick with LRFD here. So this is actually a plan, right? So we're looking down on the building. This is a floor plan. This is a steel framing plan. Again, if you haven't taken a steel design course, you might not have ever seen something like this. But this is a framing plan. You're looking down at columns, right? These are just the columns that you're seeing. And in addition, we have these beams and girders that are going to support load. Okay. What we're told here is using LRFD load combinations and applicable live load reduction, the required design moment, MU, is most nearly. So we have a beam and we have to find a design moment. So there's a lot in this problem. I kind of set it up that way because I wanted to get as much bang for my buck in one problem that I could. So if you're not familiar with loads, dead loads are kind of like those permanent loads. Live loads are kind of like those transient loads. So like you and me, we get up and leave, right? You could have a classroom full of people, or you could have a classroom that's empty. That's kind of the live load. But typically, the classroom's always going to have the floor, which is a dead load. It's a permanent. It's not moving. Okay. So if you're not familiar with loads, that's kind of the starting point. But as we come back to, if I can find it here, as we come back to the reference handbook, as we start into looking at loads here, we're given different types of loads. You could have dead, live, earthquake, wind. Typically when I am teaching my classes, I try to hit dead and live pretty hard. I'll do a little bit of snow because we live in a part of the country where we get snow here. And then there's also wind that gets thrown into the FE reference handbook. But load combinations are kind of saying, like, especially with LRFD, it's a way of saying, like, how confident are we in those loads? Like, dead loads, we're pretty confident. We kind of know what the structure is and we know how much it weighs. So we're going to say, well, if we have 100 pounds, we're going to design for maybe 120 pounds, right? So we're going to design for a little bit more than we need to be safe. So that's where we get that load factor, right? So we get a load factor. So we add maybe 20% to the dead load. But here you can see we add 60% to the live load. Why? Because, well, the live load is a little bit more unpredictable. So we have a load case, and there's a whole bunch of load cases here, but all we're given is dead and live. So if all you're given is dead and live, pretty much what's going to control is this second load case, 1.2 dead plus 1.6 live. So we can come back and we can solve for that load case. I mean, we can look at that load case. At least we can say 1.2 dead plus 1.6 live. So some of you are just going to stop right there and say, well, great, I got a load case, we're good. The only problem is this problem asked for live load reduction. I don't know if live load reduction is going to be on this or not, but when we look in the reference manual, it's on there. So if live load reduction's in here, we might as well look at it in terms of a problem, right? So this is one of those things where, especially when you get into multi-story buildings, or it's unlikely that every single room is going to be full of the maximum live load at the same time. It's not super likely. So typically what we're going to do is we're going to take, we're going to be able to reduce some of that live load depending on how much area that beam or member supports. So I'm going to take this equation and we'll pull it in. We'll talk about it. We'll solve it. But basically what this is going to do is it's going to reduce that live load down a little bit. So we're going to take L equals, and I'll just write it in here. So we'll say, let me just write it in here. So L, got to get an actual pen, a fake pen. So L equals, let me get this, L naught times 0.25 plus 15 over the square root of KLL AT. Okay. And that's not the A-team, like, we're going to drive up in a van and that sort of thing. But this is the tributary area. And tributary area in beam world sometimes is a hard concept for some people to understand. But the tributary area is just kind of like, if you were to, parcel this framing plan up. So we're looking down on this, and we put a load like maybe right here. Where is that load going to primarily be taken, right? So when we think of tributary area, it's like all the load on this beam, for example, all the load on this beam, where is that coming from? So when I think of this framing plan, especially when we get into steel design, and when this calls out something that's simply supported, right? So I think does this say it's simply supported? Maybe not, but maybe I could have put in the question that this beam is simply supported. But typically when you're looking at framing plans and you see these little gaps between the beam and the column, that means it's simply supported. So we'll go with it. So let's say these beams are simply supported. The spans kind of go this way. We're going to be able to take a look at some tributary areas. Specifically, we're going to kind of cut these two spans in half. And we're going to say, well, okay, all the load in the middle of this span over to beam one and all the load from the middle of this span over to beam one is going to be tributary to B1. I mean, I kind of maybe you think of tributaries for streams, right? Tributaries for streams. What are they? They're feeders into the bigger streams, right? They take there's a tributary rain area. All the rain that catches in that basin is tributary to that stream. Just like all the load that's kind of in this basin, this green basin that got highlighted, is tributary to that beam. So what are we going to do? We're going to call that the tributary width. And this is going to be our tributary area. So we could solve for that tributary area just to start, right? We could say that the tributary area is going to be what? Well, we're going to come halfway to this 26, so that's 13 feet. I'm sorry, yeah, 13 feet. Okay, halfway to the 30, which is 15 feet. So the total tributary area is going to be 28 feet times this span over here, which is going to be 35 feet. And we can solve that. And 28 times 35 is like 980 square feet, right? So that's our tributary area. And now we can come back and we can solve down here for the live load reduction. But in order to do that, we need one more factor, this KLL factor. This KLL factor is just one of those things that you have to kind of go look up. So unless you just remember it, if we look this up here, it's simplified. There's more complicated tables when you get into the building code, like the International Building Code, which is pretty much standard across the United States. What we have here is 2 for typical beams and girders. So we're looking at a beam. We can go with it. We're going to go with the 2. We're not at a typical column here, so we're going to go with that. And now this becomes a little bit of plug and chug. We're going to say L naught, which was, what was L naught? It was 125 pounds per square foot times 0.25 plus that 15 divided by the square root of 2 times 980. Okay. And when I do this on my calculator, I'm going to pause. I'm actually, sometimes I plug everything in all together, but I'm just going to do this one section in parentheses first because there's a catch potentially. So I'm going to do 0.25 or plus 15 over the square root of what, 2 times 980. Okay, and I do that, I get like 0.588 and 89. So I get this equal to 125 PSF times 0.589. So in other words, we can reduce that live load by like over 40%, which is a pretty big savings. I mean, when you think of the amount of steel that you don't have to provide because you're letting this come down a little bit, or you're taking the live load down, that's a pretty big amount, right? So from 125 we go down to, if I multiply that times 125, I'm going to get 73.6 PSF, right? So this equals to 73.6 PSF, and that's our reduced live load. The reason I paused here though is because if we come back to the reference handbook, right? What we see is there's some catches here. You can't reduce it so much. You know, if you have a huge area, you can't reduce it like crazy, or a small area, you can't reduce it past 40% for members that support 2 or more floors, or 50% for members that support 1 floor. In this case, I probably could have put in the problem, it's supporting 1 floor or it's supporting 2 floors, but regardless, you know, if this is a floor plan, it's probably just supporting 1. Regardless, what we see is this is greater, right? This number here is still greater than that 0.5, so it's okay, we can use it. And we can use the 73.6. So now we have our loads. And what we have to do is we have to come back and we have to take our load combination and plug it in. So let's come back, find our load combination, 1.2 times dead. I think dead was 85 pounds per square foot. If you don't have the problems, you can go down below. There's a link. You can pull these problems up as well and follow along. So 1.2 times 85 PSF plus 1.6 times 73.6 PSF. So that's going to kind of give us like a pressure, like a Q, right? And that pressure is going to be what we're going to use. So what do we get? We get 1.2 times 85 plus 1.6 times that 73.6. I get like about 220. That's about equal to roughly 220 pounds per square foot. But we don't stop there, because this beam, you know, what we see is that 220 pounds per square foot is applied over this entire green area. So we have to, you know, narrow that in here. What we have to do is we have to say, okay, all that load is going to get now taken by this beam. So what do we need to do? We need to multiply pounds per square foot by the width, the tributary width, to get a pounds per foot. And I'm going to call that W. Normally a uniform load is typically called W. So W is 220 pounds per square foot times the tributary width. What's the tributary width? Well, it's this 13 plus 15. That gets me times 28 feet, right? That's the trib width. Okay. So when we do that, I can get what? 220 times 28 is going to be about 6,150. I'm gonna convert this on the fly to kips. I'm gonna convert this on the fly, go from pounds to kips, 1,000 pounds per 1 kip, right? So I'm gonna say this equals 6.15 kips per foot. Okay, and that's gonna be our load And now we have to do one last step. So the last step is to say, well, okay, we have a beam, it's simply supported, and maybe you're familiar with this, right? I mean, if you looked at statics, what we have is a beam that's simply supported. It's got a uniform load, right? And this uniform load is 6.15 kips per foot. And do you remember what the moment is? Let me put it in the chat box if you do. This is one of those questions that one of the reasons I did this question in particular is because I think this is one of those basic structure diagrams that's going to be probably tested somewhere along the line. A simply supported, uniformly loaded beam is one of those beams that, if you know what the moment is, I think it's going to help you. I think it's going to be beneficial. Does, you know, if you know, I'd look for hands if I saw hands, but I don't see your hands, right? I mean, maybe you're raising them online virtually, but who knows? What is it? MU, oh man, is WL squared over 8. And you're like, that's great, but that's magic. I don't know that. I never took a steel design course in my life. So where can you find it? It is in the reference handbook. I think this is one of those ones that if you commit to memory, it'll probably come up. Okay, but where can you find it? If we come to the reference handbook, it's actually not in the structures section. We have to, I think it's back in the statics and strength materials section. So this is where it helps to know the manual a little bit, right? So if we know that, okay, wait, there's some beam diagrams back in the statics, mechanics and materials section. Is it mechanics and materials where it is? Let's look. There's some beam diagrams in here. If you know where to find these, it's going to help you potentially, right? So what do we have? We have a uniformly loaded, simply supported beam. And that's where we get our moment at the max is WL squared over 8. Okay, so if you don't know that by your own, own memory, this is going to help you as well. So, yeah, that's awesome. So let's go with it. Let's go with the WL squared over 8. And what we get is this is going to be equal to 6.15 kips per foot times. What's the length? The length is going to be this total span. So the total 35-foot span is going to be the length, right? That's the length of this beam one is 35 feet. Okay. So what does that look like? 35 feet. And we have to square that and divide it by 8. And we get MU equal to, let's see if we did it right, 6.153 times 35 squared divided by 8. I got about 942 kip feet. And we get kip feet in moment. That's good. That's helpful. We get this 942. What we're hoping and praying is that when we come back up, we hit something that's close to 940, and when we see that there. So good news is we get an answer that should be right. Okay, if you didn't go through the whole live load reduction, I think that might give you one of these other, I think that might give you, I can't remember if it's this one or this one, but if you don't go through live load reduction, you get a bigger number, and it's wrong. So even though you might know the whole thing, if you didn't do the live load reduction, you kind of missed it. But the reason I wanted to bring this question in is load combinations are going to be on there. I think this basic 1.2 dead plus 1.6 live is the most basic load combination, and I think that's one that could be tested. Live load reduction, maybe not. But this idea of tributary area, tributary width, it could be. And then this idea of just simple static shear moment diagrams, WL squared over 8 type of thing, I think could be there also. So, I picked this problem because I think there's a lot in it. And this is probably more than a 3-minute question. But I think it's potentially parts of it will be there. Maybe it's not the whole question. Maybe they don't ask you for the moment, but maybe they ask you what's the design line load or something like that, right? And you have to go through live load reduction and the load combinations. Maybe they give you live loads and they say just without live load reduction, they're asking you to solve for this MU or something like that. But this is kind of the fundamentals of load combinations, shear moment, that sort of thing. And I think those will be on there. All right, well, 1 down. Hey, let's keep going. Okay, and 2, the favorite question of the seminar. I don't know. Actually, this question is kind of interesting because I was doing a question like this in a steel design review type of thing, and I looked in the reference handbook. I think last year or the year before, and the reference handbook actually had a mistake in it. So we'll take a look at that. But the good news is version 10.1 now has an updated problem or updated equation in it. So I sent NCS an email at one point and said, hey, I think this equation's wrong. I kind of teach steel design, and here's the code. And they actually went back and changed it. So that's good. So if you do find mistakes, and they do happen in the reference handbook, definitely reach out to NCS and ask. So those things do get updated. But here what we have is a plate. It's loaded in tension, and we got some bolt holes, right? So these bolt holes are there. They're 3/4 inch diameter, and the bolt holes themselves are 13/16 inch of diameter. You want a little bit extra there so the bolts can fit in. The bolts can fit in. So they're loaded to resist tension, and the plate is ASTM A36 steel, and I just give you the yield strength of 36 KSI and the ultimate strength of 58 KSI. That's in the manual. You can go look it up. It's in the mechanics and materials section. Maximum tension force that this plate can resist based on, and this is key, based on yielding and net section rupture only by LRFD is most nearly. So what that is doing there is it's sort of limiting the problem. We could take a look at this problem, and we could look at bolt strength. We could look at bearing and tear out and shear. We could look at block shear, right? But what this question says is just yielding, just net section rupture. These are kind of two of those kind of basic ones. And I think I when I'm looking at tension steel components, I'm thinking, and when I'm looking at steel components, I'm thinking tension member, compression member, like a column, we'll do a column, and bending, and we'll do bending. So those are the three that I'm thinking of for steel. So we'll do one of each of those. So let's take a look at this tension member here, right? So let's just look through, let's look through both, right? So what's yielding? Well, yielding, I don't know, maybe you took a mechanics course where you had to go to a lab and you took a steel coupon and you pulled it until it broke and the thing knocked and you had a stress strain curve and that sort of thing, right? Do you remember those stress strain curves, right? The stress strain curve looked like this, right? So you have sigma on one side, epsilon on the other. And with steel in particular, you have this linear elastic portion, and then it yields, right? So it starts to yield, and you get this strain hardening, you get this plastic plateau, you get some strain hardening going on, and then eventually you get to rupture. That's one of the reasons steel is so great, because it has this, it has a lot of ductility. There's a lot of bending and permanent deformation before it fails, so you can see it fail, it can absorb a lot of energy. But two of the points that we're gonna deal with here are this is going to be our yield strength, our FY, and then we're going to also have our FU. I'm not being mean here, but the FU is going to be the ultimate strength of that steel. So as the steel gets pulled, it actually gets harder and can resist more stress. So what happens here? Well, a yielding failure is going to be kind of at this point here. It's going to be okay if the gross section area is just going to yield, it's going to move too far and eventually break. Ultimate strength is up, at this point up here, and that's actually going to occur typically through the bolt holes. So we're going to take a look at those. And to do that, let's just come back to the manual for a second. So if I come back to the manual, come back to civil engineering, and specifically, if I come way back down to structural design and go past the load combinations, eventually we get past the snow loads, past the wind loads. They could be on there, but we get to beams, we get to shear. We're in concrete. We'll talk with concrete next, or about concrete next. But then we get to steel design, beams, columns, and down here, not forgotten, our tension members. Okay, so what we have here are tension members, and specifically we get limit states of yielding and rupture. Yielding is going to be PN is FYAG, and rupture is FUAE. So let's just come back here. We'll write those down and we'll take a look at them, right? So we'll go through and solve each. So yielding is going to be PN equals FYAG, and I think we said rupture. Those are the two limit states that we had to look at. PN is going to be FUAE. And if this equation is, it's just an equation, you don't know where it comes from. If you remember, going back to kind of these fundamentals again for a second, do you remember the idea that axial stress equals force over area? It's kind of one of those basic equations. We talked about it in strength of materials. This equation if you solve for force, right, what's the maximum force? You're just going to get a stress like Fu or Fy times an area, right? And that's kind of where both of these come from. Okay, and that's where we're going to go now. So what do we have to do? We have to look at each of these and solve. So with yielding, what we're going to do, we already know Fy, that's just 36 KSI, that was given in the problem statement. And the AG, that's the gross area. So this is, when we think of area, let me draw a little sketch in here. So if we consider this plate having failed or failing, yielding says we're going to fail it kind of out on this surface way kind of out here. So not at the bolt holes. This is going to be our gross area. Okay, and rupture says, okay, we're going to take a look at that, but we're going to take a look and we're going to say that this thing is going to fail. Let me draw this better. It's going to fail through the bolt holes. I'm trying to get that 3 dimensions going. I know, yeah, it works. But when you get those 3 dimensions going, what you see is once we cut those bolt holes out, the area becomes limited, right? So we have to subtract that bolt hole area out. So this is going to be essentially, this is going to be our net area. And the net area is a little bit different. You'll notice that N and the E are different. It's different by this factor U. U is a shear lag factor. It's sort of like if you pull on a plate and only hold it in one spot, right? If you pull on a plate and only hold it in one spot, this part's floppy. It doesn't resist tension. So that's where there's this idea of shear lag, and there's this U factor such that we know over here that actually we get FU times U times the net area. Okay, if you don't know what U is, there's an equation for it. It's okay, you can come back to the reference handbook, and there's an equation for it here. You can find your equation and solve it. Okay, I'm not going to get into U today. I'm already probably going to spend too much time, but what we're going to do is we're going to take a look through here. So let's first go to the yielding, and we'll come down here. So what I get here is I'm going to say Fy times Ag. What's the Ag? Well, this plate is going to be a total width of, we have 10 inches by 1/2 inch. So we're going to come back here and we're going to say 1/2 inch by 10 inches. And we get Pn equal to what's 36 times 5. So 36 times 5 is going to be like 180 pips. Okay, and let's do the same thing over here. And if you don't know what AN is, that's okay. There's actually an equation for that. And this is the one that was recently updated in version 10.1 of the reference handbook. So if we come back to, I'm not scrolling too wonderfully here, but here we go. We have the net area for parallel holes. If you have staggered holes, you have to add this S squared over 4G term in. Again, if you don't know what that is, we can do another video. But at first, we're just going to do this basic idea here of this AN is BG minus the sum or sigma of DH plus 1/16, right? So let me write that in. Let's just first solve for AN. So AN equals, I wrote the formula down here. So BG minus the sigma of DH plus 1/16, and all of this is going to be times the thickness. Okay, so what does that mean? Well, AN, this is going to equal 10 inches. That's the plate width. So BG is the plate width, right? So that's this distance here. That's 10 inches. Okay, and then we're going to subtract off the sum of all the bolt holes plus a 16th. So the sum of kind of these bolt hole diameters here. And can I get this in here? I don't know. Maybe I can. But this is your DH. That's your bolt hole diameter, right? So we're subtracting out that area. So what does this mean? We have 3 bolt holes, so that's going to be my sigma part of it. There's going to be 3 bolt holes here, okay, times the bolt hole size. And if you remember, we said the bolt hole size here was what? 13/16. So the bolt hole size is 13/16. We've already added a 16th, but we have to add another 16th here as well. So we're going to come down. We're going to take 13/16 and add another 1/16. And then we're going to close our brackets here and multiply it by 1/2 inch thickness. So we get a net area of, I think, 3.6875 square inches. Okay, so once we have that, we can now come back and solve our PN. PN is going to be FU, which is 58 KSI, times 3.6875 square inches. And we get PN equal to, what, 58 times 3.6875 is going to be about 214 kips. So it almost looks like a no-brainer. Well, we're going to take the smaller of the two, right? Let's think for a second. What does LRFD say? LRFD says phi PN has to be greater than or equal to PU. In other words, the provided strength has to be greater than your required factored load. Okay, and that's going to be what we need to look at. And you might be thinking, like, well, phi is phi, isn't it? I mean, phi is just a number. It's a reduction factor, which is true, but phi is not the same for yielding and rupture. So let's come back here and take a look, and we'll see here. So if we come back down to tension, what we see is for yielding, phi is 0.9, for rupture, it's 0.75. So let's come back and plug those in, and we get phi PN, right? We get phi PN for yielding. Phi PN equals 0.9 times 180 kips, and that's going to equal, I think, 162 kips. And we get phi PN here for rupture, and that's going to be 0.75 times 214 kips. And you know what that's going to be? It's going to be 160-ish. I mean, it's going to have some decimal there, but it's going to be 160. The smaller is going to control. So because we get this bigger reduction factor, the smaller rupture is going to control over tension. So we come back up, and we see that we have a couple of values here. We got we do have this. This is the yielding value, right? But the controlling, right, the maximum force it can resist is going to be the controlling one, which is going to be our rupture, because in other words, this plate will essentially rupture before it yields. Does that make sense? It'll hit that 160 before it can yield at 162. Pitch and gauge, yeah. So if we had staggered bolt holes, so let's say, good question. I mean, honestly, if we had staggered bolt holes, we'd have to adjust our net area here. So for staggered bolt holes, we'd have to add back in plus sigma s squared over 4g. And you might be thinking, Mattson, what's that? If we come back here, there is an area formula here where we have this plus s squared over 4g. That's the only difference in these two net area formulas, that is s squared over 4g. So pitch and gauge is important. And when we come to the manual, though, the one interesting thing here is it tells us s is the longitudinal and g is the transverse spacing. The way that I think of that is this. So if we have pitch and gauge, if we have to add something in, let me just draw it. I don't know, I'll draw it down here. So if we have to add in, like, let's say we had bolts that had some stagger to them, not like drunk stagger, but like just stagger. Okay, let's say they had some stagger. You have to know which one's S and which one's G. The way that I like to think about it is typically G is down. Right, G goes down, gravity goes down. That's the way I kind of remember it, and S is this way. So if you have bolts that are staggered, your failure plane is going to be a little bit bigger, so your area is going to be a little bit bigger. That's why we're adding this back in, right? Because we have to have that pitch that's going to add in some area. Does that make sense? So that S squared over 4G is going to add in. So S is the longitudinal spacing, G is the transverse or vertical spacing. And if you remember G, gravity goes down, that should help you as well. So we didn't get into that problem, but it's a good question. Could it show up? Sure, it certainly can. But at least gets you into the basics. I say the basics. There's a lot here. This gets into the basics of yielding, of rupture, of some of these areas. And I like drawing these figures here because it helps you to hopefully picture the gross area versus the net area. And that's a kind of a fundamental concept when you come to steel design. All right, we're just rocking and rolling here. So let's keep going. Thanks for the questions, by the way. I appreciate them. As far as TR55, hey, in a couple of weeks we'll be hitting H&H, so we should get back on some of those things, but we're not there yet. So okay, how does he know that U is 1? Good question. I can come back to that. I do appreciate the questions. How do I know that U is 1? So this will be another really bad joke. You can call me Mark, you can call me Mattson, or since we're doing steel, you can just call me the Man of Steel, Superman himself. That was a joke. That was not real. But actually, I had a friend who, like, my kids asked him, what should we call you? And without blinking, he just said Superman. So you guys can remember that. How do I know that U is 1? What we have here is a flat bar. Okay, we have a flat bar. And that's it. So since we have a flat bar, U is 1. If we had something like an angle that was only connected on one side, I love Judy Liu from, I can't remember what university she's at, but she has this great teaching video. Maybe I'll put a link below. But it shows shear lag. The idea that if you're pulling on an angle, right? So if this is like an angle and I'm pulling on it, there's part of this paper that's not in tension, right? Most of it's in tension, but there's part of it that's not. And that's kind of the idea of shear lag. It's the idea that if it's not in tension, you're going to subtract off, you're going to reduce that net area a little bit. So if you have like angles or channels or something like that, and you got one leg that's connected and one leg that's not, you're going to use this 1 minus x bar over L, and you're going to have to go look up x bar where in the shape properties, and L is going to be the length of the connection. Okay, so good question. If you get into welds, you get some other things going on as well. But since we're at a flat bar, it's easier. That's kind of the fundamental piece of it. All right. So let's keep going. Let's keep going. Question 3. A W12 by 58 steel column with FY 50 KSI is an effective length of 30 feet about the strong axis and 12 feet about the weak axis. So the available compressive strength of this column, VPN by LRFD, with these effective lengths is most nearly. Okay, so let's just draw that column kind of quickly here. So if we have a column, right? And I'm going to draw this column twice. Okay, so we have a column, and I'm going to label 1 the strong axis and 1 the weak axis. Okay, in other words, if you have a W shape, one side of that W shape is going to buckle more easily. Just like if you have a piece of paper and you push down on it, you're always going to get buckling in that weak axis, right? You're always going to get buckling in the weak axis. If you brace it, you'll get this double buckling thing going on, right? This double buckling thing going on. But basically what we're saying is in the strong axis, we have an effective length here. So this effective length of 30 feet. And then the weak axis, we're going to brace it. So sometimes you'll see this in a like a building, like a field house, like at the school where I teach. There's a field house, and there's columns that go from floor to ceiling, and in the middle of those columns in the weak axis, there's braces, but not in the strong axis because they would go into the field house. Right, but so what we have here is we have 30 feet, and we have another set of kind of like maybe I'll put rollers here that limit the effective length in the weak axis to 12 feet. Okay, so in the strong axis, this thing's going to buckle kind of in a strong way, and this thing in the weak axis is going to buckle, a little bit differently. Okay, a little bit shorter. So the strong axis is going to be, we don't know which one's going to be stronger. But what we do know is we have a W12 by 58 column. We do know that we're looking for VPN. And the good news is there's a table for that. So we can come back to our reference handbook here. And if we come back to columns, we sort of find it, but we sort of don't. So if we come back to columns, we have these values here, so we could plug in chug, but I'd recommend not plugging in chugging because there's a table, right? So there's a table here that we can use, and specifically here's some of those shapes, those shape properties. So it's funny, actually, they don't even show an X bar here, and that's partly because this is a symmetrical section. So I'd be shocked if you get a 1 over X bar, 1 minus X bar over L problem unless they give you X bar. Okay, but as we come in here, we see some bending, some more bending moment. And then we get into these effective lengths, and that's kind of cool, but are we going to get into moment frames and that type of thing? Effective lengths, having to go find K. I don't know. I mean, could they ask you? Sure, it's in there. We also get to hear F or phi FCR, so this is critical stress. That makes using those equations a little bit easier. But then we get to this table, and this is the table that we can use here, because we get available strength and axial compression. We get phi PN. That's exactly what we're looking for. So we have a W12 by 58. Hey, it's even in the table, right? All we have to do is we have to come down and say, okay, we got 12-foot bracing. We got 603. We're done, right? Or do we come down to 30 feet and say 187? Well, if we come to 187 and you say, let's just use 187, look, there's a 190 and there's a 600. Is the 190 right because it's smaller? Or is it wrong because it is wrong? But do you know why? If we look at this table, it's easy to look up a table, especially if you haven't done steel design, and think like, oh yeah, I could just look up a number, find a number, and use it. But one of the things you have to understand with this table is the effective length factor is with respect to the least radius of gyration, Ry. So that's going to be for the weak axis. Okay, so that's going to be for the weak axis. So this table's only valid for the weak axis. So this is only valid for that 12 foot for the 603. So then you think, okay, do we stop and just pick 603, 600? I mean, that's pretty close. But hold on, let's just write that number down here. So what we know is we know that for the weak axis, from the table, what do we get? From the table, phi PN equals 603 kips, at an unbraced length of 12 feet in the weak axis. And so that's one number. Do we stop there? If maybe, but no, you can't stop there. You have to check the strong axis as well. So what do we do with the strong axis? Well, we can go back and use the equations, or we can adjust. And what I would say is you adjust. Honestly, one of the best ways to do this, I would say, is take your KL and you get your KL Y equivalent. Right? So this is your KLY equivalent for the strong axis. And to do that, what we're going to do is we're going to take KLX and multiply it by RY over RX. So this is going to get you, essentially, we're going to take this value and multiply it by RY over RX, the two different radii of gyration, and get an effective equivalent KL that we can use in that table. So if we do this, we have to figure out what RY and RX are. But we should be able to do this, right? So unfortunately, it's not listed in this table. In the steel manual, it actually is. But we can come back here, and it's not too far to go and find it. If we come back to our shapes, we come to a W12 by 58, all the way kind of at the bottom here. We look at R. We get RY of what, 2.51. We get RX of 5.28. So 2.51 and 5.28. So now what we can do is we can say, well, this is going to equal 30 feet times 2.51 divided by 5.28 inches. The inches cancel out, and we get an equivalent effective length of, I think that works out to about 14 and a quarter feet. Let me just double check that. 30 times 2.51 divided by 5.28. Yeah, I get like 14.26 feet. And the reason that's helpful is we can use, this value, a KLY equivalent, in the table, right? So that's gonna help us. It's gonna help us because now if we come back to our table, we can go back to this table and we can use the table, and we can say, if we have this W12 by 58 here, at 14 feet, we know it's what, that's like 553, or at 15 feet, it's 527. So what we can say here is, at 14 feet, we have what, 553 kips. At 15 feet, we have 527 kips. And we don't even have to go further. You could do linear interpolation, but why? On the FE, you don't have enough time. On the FE, what you're trying to do is you're trying to get the right answer in the least amount of time. So what we see here is the 550 is pretty much spot on, okay? And that's the value that we're going to use here, because this is, if we have, this is our weak axis strength of 600. Our strong axis is actually less, okay? And the strong axis is less because you have a bigger unbraced length, okay? So the reason I threw this one in there is partly, one, to help you know how to use the table, but two, to kind of think about that concept of unbraced length, because this is where you're going to buckle in one way or another. So is there a symbol for unbraced? Typically what I would do here is I would just, I might throw this in as a pin connection on the top, a pin connection on the bottom. All right, so that's going to give you kind of like a column that's unbraced for 30 feet. And the reason pins work nicely is because if you come back to the reference handbook and we come back to the column section, so let me come back up here. So just come in, so there it is. It's the column section. So if we have a pin connection, we get that K value of 1. We have fixed, it goes to 0.5 theoretical or 0.65 for design. So but the K of 1, that's a pretty basic one. That's pretty basic. So that's what you said. You said at something. So let me look back. I don't know what I said, but you can go check the recording. So the unbraced length. So I told you the unbraced length here. So I told you we have a 12 by 58 effective. I said effective length of 30 feet about the strong axis and 12 feet about the weak axis. So that's that 30 feet effective. That's that KL. So this is going to be like a KL. This is, if I were to write that in, this is like KLX. This is like a KLY. So typically, we're just if we're in this question, you have to what did I write? Where did I write it down? You said at. I don't know. LB. Sorry, there you go. The LB is the unbraced length. We'll deal with that again, and when we get to moment in a second. But typically, we're gonna come here. So if you're the question, what do you use? It depends, but theoretical, if we're looking at theoretical strength, we're going to look at this K value. If we're looking at the recommended for design, if we're actually designing, we're going to come into here and use the recommended values. So where did I get the ROI over RX formula? Oh man, I got that one from my brain. I'm sorry. So this is where the manual's not going to tell you this one. I hate to say that one, but if this is if this table is based on RY, we need to convert it we need to convert the X value to RY. So if you think, how do we get to RY? We multiply by, we divide by RX to get rid of the impact of RX, then we multiply by RY to get to the equivalent RY. So it's just, that's one of those ones. I hate to say I just know, but oh man, because I hate to do that to you. But it's like some of these things you're going to have to, if you internalize, it's going to help. But column strength, I think, could be on there. Are they going to, maybe they just give you weak axis straight up. Okay, if they give you weak axis and strong axis are at the same length, right? If you get a problem where you know that, the weak axis and the strong axis, right, are both the same, the weak axis is going to control 100% of the time, right? Just like, right, if they're both the same, if they're both 12 feet in the strong and the weak, we're totally going to get the weak axis is going to control. Just like if you take this piece of paper here, which happens to be my CRSI chart for concrete values, but it's always going to buckle on the weak axis if everything else is the same. So if the strong and the weak are the same, you don't have to worry about it. Maybe they won't go there, maybe they will, but I wanted to get you thinking about that a little bit, because I think it's one of those things that's probably worth knowing and not having to go use the formulas. Okay. Hey, let's keep going to bending. Okay, so bending, design of steel components, bending. What we're going to have here is we are just going to jump in with this. What we have is a simply supported, uniformly loaded, and braced laterally only at the end. So we have a beam that's simply supported, uniformly loaded, braced only at the end. So this goes back to the idea that simply supported beam, right? It's a simply supported beam. It's uniformly loaded. And here I'm not giving you the load. I'm not saying go find MU, but I am telling you what this beam looks like. I'm just telling you that this has, this is an 18 by 55, right? So it spans, what did I say? It spans 12 feet. So 12 feet. This is, what did I say? This is a W 18 by 55. Okay, so the question is, well, the other thing that I tell you here is it's braced only at its ends. So braced laterally only at its ends. That's a big deal because as we, again, I'll take my little piece of paper here, but as we bend this thing, what's going to happen? The top is going to, I don't know if you can see that, but what happens when I try to bend this? When I try to push the top in, what happens? The top goes into compression and the top buckles, right? So if the top buckles, that's a case of lateral torsional buckling. So this is where we come up with that other term. This is also known as LB, the unbraced length. Okay, so this is an unbraced length that we have to be aware of. This is called, what did I say? I said it's braced laterally only at the ends, but this is the unbraced length, okay? And that's gonna be critical to the moment strength. Actually, it's really critical to the moment strength. And one of the things with steel is it has a huge strength, but sometimes what happens is it buckles before it reaches the strength. So if we just knew this thing was laterally braced, we could go into the manual and we could say, well, MN equals what? MN, if we come back to the manual, right? MN equals, we could just even come to this table and we could look up and find VMP, VMR, and then this VBF, which we could do, but we'll find a better way to do it. We can come in here and we say, well, if this is laterally braced, we're just going to use FYZX. Laterally braced, no problem. We're going to get the full strength out of this thing. If it's not laterally braced, we have to come in and use another equation. This equation just looks ugly. So what I'm going to say is don't go use that equation. Do a simpler equation or do a simpler process. In this simpler process, again, and this is where if you know the AIC Steel manual, you're going to use some of the tables in the manual, and you probably learned how to use the tables in the manual. One of the tables tells us the value of CB. We'll come back to CB. That's a lateral torsional buckling coefficient, and it doesn't say lateral torsional buckling coefficient. It just says CB. Okay, but this shows different bracing points. So we might be braced at just the ends. We might be braced, at the load points. In here we have a uniformly loaded. It says none, but you see these little X's at the supports. That means it's braced at the supports. So in addition, we get some other values here for the midpoint or additional like third points or quarter points. But what we have is we have this thing braced only at the end. I'm gonna take that CB value of 1.14. Let's take a look at that. So MN is what we're trying to solve for is VMN. Okay. So what we're going to do here is I just said, well, for this unbraced length supported only at the ends, we're going to say CB equals 1.14. I think that's great, Mattson. How do we get the strength? That's what we came to do with solving this problem. So let's go solve it. Okay, so what do we get? Well, again, we're going to keep coming down here. And this is where sometimes the tables are past, in the way the manual is set up, the tables are past where we are. We get VMP. What's VMP? What's VMR? What are these different points? And let's take a look at that for a second here. Actually, let me just draw something out here. The way that bending works in steel beams specifically, right? So we have bending and we have moment strength and we have the unbraced length. This is that LB again, unbraced length and moment strength. And the way bending typically works in a steel beam is we start with some value up here. And then what eventually happens is it buckles, right? So we have some value and this beam is solid, and then eventually it I don't know if you can see, but it buckles, right? This beam, it doesn't really look like a beam, but it buckles. So the strength, even though the beam is really a pretty strong beam, because it's so long, that top that's in compression, right? And with beams, you have tension on one side, compression on the other. The top that's in compression is going to buckle, and it's gonna the strength is going to go down. So basically, the way that this works is with steel beams, we have this linear portion, and then we have a kind of a buckled portion. And this looks a lot like what happens with steel columns. You get a squash load, right, when it doesn't buckle. And then eventually when the column gets long enough, it starts to buckle. It starts to go out of plane and buckle. Okay. So that's where, like, this column is going to buckle eventually. It's going to go out of plane and buckle. Okay. That's what's going to happen with beams as well. So we're going to get a couple different sections, right? We're going to have a section for the full plastic strength. This is going to be MP. We're going to have, right, so this value up here is going to be MP. This is going to be the full strength, no buckling. Okay. Full capacity. Actually, let me erase the MP down here. Full capacity, no buckling. Okay, so that's this point. That's that FYZX term, right? So that's this first equation for FYZX. That's that MP, that first value, and that's good up to a point of LB equals LP. So there's this LB equals LP. What's LP? LP is this point here. And then what's going to happen? Well, then it's going to buckle. And if I move my LB term down a little bit here just to make a little bit of room, it's going to buckle, and it's going to buckle in a couple different ways. I'm going to call this point LR. There's two different buckling. This is the full strength, and then it's going to buckle. And there's inelastic buckling, and there's elastic buckling. And do you need to know all this for the test? Probably not. But I want you to see the big picture here, because I want you to see some of what these values are, because I think it's gonna help you a little bit when you get into a problem where it asks for bending strength, right? Because eventually, what you're gonna do is we want to go look this up. And the nice thing is, for each beam that they could ask you, there's probably gonna be a table in the reference handbook. So if we come to the reference handbook, what do you see here? You see some of these tables, right? And what do we see? Well, we have an 18 by 55. Right? Oops, let me zoom that out just a little bit. We have an 18 by 55, right? So here's our 18 by 55. We have this little short section that has a plateau on it, and then it starts going down at a linear, linear. And eventually, if we kept going off the chart, it would get to like a curving slope. So the nice thing is we have an unbraced length, 12 feet. We can come up here. Actually, let me switch over for 1 second. I think I have this on another one where I can draw on it a little bit more easily. So I think this was 258, maybe, I don't know, somewhere in there. No, not there. I think I need to keep coming. Sorry, I thought I had this written down. I do. It's 292. So let me go there. So 292. So if I go to page 292, the reason I wanted to bring this up is because it's easier on this version platform for me to come up at 12 feet here until I hit this W18 by 55, right? And if we want to highlight the W18 by 55, I can do that as well. Here's my W18 by 55. Here's my W18 by 55. So what I'm going to do is I'm just going to draw a line up till I hit that W18 by 55, and then I'm going to draw my line over from that point, to the left side where I have phi-mn. So phi-mn, if we're in between 330 and 345, each one of these is going to be what? 330, 333, 336, 39, 42. So this is going to be 339. No, I'm sorry, 336. 336. 336, if I do that right. Okay. That's going to give me a value of 336. So the cool thing is, if we were to look at if we were to come back into here and we were to say, like, okay, that's great. So we know our phi-mn value from the table, and I'll say see, page 292 of the handbook. See, so if we look at that, we get, unbraced length at 12 feet. I'm going to say LB again, that unbraced length, LB. We got 336 kip feet. And everybody's happy because that number's in here and you've already talked long enough. Oh, but that's the wrong answer. And somebody's thinking, well, why is that the wrong answer? We just looked it up, didn't we? Didn't we get this? Didn't we get this right? Let's look at it. And if you come back here, yeah, we did this right. That's 336. So what gives? Well, what happens is that this chart is valid for a CB of 1. So if we look up here, right, we have a CB of 1. What we actually have in this case is a CB of 1.14 because we're only braced at the ends. And if the problem ever says if it says it's continuously braced, CB is going to be 1. Continuous bracing, CB equals 1. I doubt they're going to ask you to go calculate CB. It's probably going to be a lookup. To calculate CB, it's a longer kind of formula, but I imagine there's going to be like, you know, if they give you something, they'll give you an unbraced length. And in this case, CB is 1. So what do we do with CB? Well, what CB does is if we come back to the table here for a second and we look at our equation, what you can see is that CB value is an increaser. It's a multiplier increaser. So it's going to increase our strength and as long as it's less than MP. Okay, so as long as it's less than that top end, we can increase it. So what that looks like over here is that's going to say this is kind of going to do one of these things where it's going to increase this chart kind of by 1.14. So it's going to make this thing go up kind of like by 1.14. And what we want to do here is I'm sure I didn't draw this to scale, but this is going to go up, you know, essentially by CB equals 1.14 because we looked that up. So let's come back to where we were. And what we'll do is we'll say, okay, but with CB equal to 1.14, we get PMN equal to 1.14 times 336 kip feet, which equals, I think that's 383, I'm guessing. 1.14 times 336 is going to be 383 kip feet. And if you remember that the equation, it said it has to be less than, it said less than MP, but I'm going to throw the phi in there as well. It has to be less than phi MP. What's phi MP? Phi MP is that top end, right? That top end. And if we come back to our chart here, what we can see is that top end is going to be 420. Okay, that's the top end that we can't go past, and 383 doesn't go past 420. So we're good. So we get 383 here. And this introduced, the reason I use this question is it definitely introduced a lot of different concepts. It'll introduce the whole concept of bending, whether it's continuously braced, you're just going to get that MP formula. So continuous bracing, that's just going to be FYZX, okay? Sorry, I wrote ZZ, but ZX, okay? And if you get into lateral torsional buckling, where that top cord wants to buckle out of plane because of the compression, you possibly could look at CB equal to 1, or you get into this case where if CB is greater than 1, this whole curve is going to shift up, right? This is going to shift kind of up by CB, okay? Oh man, and now some of you are wishing you took steel design, but it's okay. Maybe you're glad you didn't take steel design and you're doing transportation. But the thing is, you want to do steel, you want to know enough steel design so that you can figure this out. Okay, good questions. Where did I find the 1.14, and where are the elastic versus inelastic zones on your graph? Okay, so this is so if we come back here, so first I'm going to do the second one first, and then I'll come back to CB. So LP and LR, these are the transitions from the plastic. The full plastic yielding or plastic capacity MP, the full plastic capacity MP. And the buckling, so that's the first transition. Then the second transition is from inelastic buckling to elastic buckling. Elastic buckling is like you buckle it just like I can buckle my little ruler here. I can buckle my ruler, it'll spring back. It's elastic, right? It's elastic buckling. It doesn't stay deformed. Whereas inelastic, it stays deformed. Okay. Where are those points? They're big long formulas in the code. All right, and they show up kind of here. But really, the FE is not going to make you calculate those. If you need LB or LP, you can look them up in this table. So LP and LR are in this table. They're going to give you LB. You're going to be given LB. So LP and LR, these are here. They're a lookup. So LP is 5.9 feet and 17.5. So we're right smack in the middle of that. So LP, we said was like 5.9 feet or 17 point. I don't remember what I just said. 17.5 feet. Okay, so we're right smack in the middle of that with 12 feet, which is actually makes sense because when we look at our chart here as well, 12 feet is to the right of the 6 feet. We see that transition point at 6 feet, and 12 feet's kind of in between that. And if we were able to get down to 17, we'd see this thing start to dip a little bit and curve. So the next question was, where did I get CB? And again, that's a lookup. There's a formula for it, right? So there's this formula up here. I'd be shocked if the FE makes you do that formula. If they do, you have to look at the moment curve and all that sort of thing. And as soon as I say this, I'm going to get a comment below probably saying, I just took the test and CB was on there. But I don't know. I think honestly, my personal opinion, because normally when I'm teaching this, I don't make my students calculate CB like more than like once or twice, right? The fundamental thing that I want them to know is to go look up that CB value. And where did it go? It's there's a table for it. It's in the manual in one place. Oh, here's the, yeah, so here's that CB value. Here's that CB table. Okay. And this just depends on the condition. If it's a uniform load, where's their bracing? Is it just at the ends? Is it at the ends in the midspan? And there's different values of CB here. And you'll notice even here, this is like 1.45, 1.01, 1.45. By the time you get to fully braced, your CB is just going to be 1. Okay, so this is a lookup in a table, and that's it. I mean, if you can look it up, if you know where to find it, that's where you get it. So I hope that one helps. I mean, it's like, again, it's like I wish I could teach a whole steel design course like right here, but I got like an hour or two to kind of try to download like the fundamentals of steel design. But with bending, the biggest thing with bending is if it's not continuously braced, you don't have that full plastic section capacity. You don't have the MP capacity. You have to start looking at lateral torsional buckling. And lateral torsional buckling, it gets into the curves, but it also gets into that CB value. So there's a lot there. There's no question there's a lot there. But I think this is the kind of the basics. Say the basics. There's like, we just spent 10 minutes, whatever. There's a lot there. But especially if you haven't taken a steel design course, and not everybody has to, it might be more confusing. But hopefully this kind of gives you at least an intro into the steel bending design. So we did tension members, we did compression members, we did bending, and we're gonna just keep going here to concrete. And now we get one of those questions that you all love and hate. Those conceptual questions, right? This is not a question. This is one of those questions where you make up time, hopefully, because it's a 30-second question. You read it, and hopefully you don't get it wrong. Now, the problem is when I ask this question every time I'm doing concrete design, 90% of the time people get it wrong the first time I ask it. So that's why I think it's a good question for the FE, because not because they're trying to trick you or trying to get things wrong. But here, what they want on the FE, in my opinion, is that they want you to know the basics, the fundamentals. And here we ask, I ask, when designing reinforced concrete beams to behave in a ductile manner, the reinforcement should generally be, what's ductile? Ductile is that you get that long, plastic plateau, that, remember the steel curve, we have that ductility in the steel where you get a lot of deformation before a failure. So why do we want that in concrete? Because we want to see the beam before it just explodes and fails and falls and kills people, right? And we don't want that to happen. We want to see a ductile failure. We want to see ductility in that beam. We want to see that thing starting to fail before it actually fails. So what does that look like? Well, what that looks like here is we're gonna have, let's just go down through these. Do we want it over reinforced? No. Okay, so over is just bad. I mean, I shouldn't say that. It's like normally when you're thinking structures, well, yeah, we want over designed, right? Well, kind of, sort of, not really. I'm an engineer who would say I'm an expert at designing beams that just barely work. Why do you say that? Well, because we don't want beams that are so huge that they're ridiculous. But in concrete especially, we don't want beams that are over-reinforced, because that makes them, instead of tension-controlled, failing. I keep doing this because I see the failing in tension in a ductile way to failing in compression. And when concrete fails in compression, it explodes. Okay, it can explode. And it can be very sudden. So if we have over-reinforced, if we have too much reinforcing, we get away from that ductile failure and we get into a brittle failure, and we don't want an over reinforced beam because we don't want a brittle failure. So no to a brittle failure. No, this brings with it a brittle failure. Okay. So we want to balance. I mean, let's not go too far one way. We don't want it under reinforced, right? But the reality of it is that we don't want to balance either. The code wants to make sure that the concrete is going to fail in a ductile manner, and the only way to get there is to use a beam that's actually called under reinforced. So the answer here is going to be under reinforced, and it doesn't mean that it's not reinforced strong enough to hold the loads. Typically, under reinforced indicates that it's reinforced in a way so that there will be a tensile failure. This means this indicates, right? So this one here, this indicates a tensile failure. Okay, and that's what we want. We want this beam to fail ductily. We want the steel to yield first and have that big long strain hardening phase, so we see what's going on before the thing just explodes and falls and kills people. Okay, so we typically want what's called an under reinforced beam. Okay, and it's not like saying it's not designed sufficiently, but it's, and maybe I could write this differently, and I could write this in terms of, if I gave some different answers, I could say compression controlled, or compression controlled, tension controlled, A, B, and C, or compression controlled, balanced, or tension controlled. And really, what we're saying here is that the under reinforced gives the tension controlled failure. So I don't know if that makes sense. Hopefully it does. But the idea is we want this thing to fail in tension. We want to see the steel yield before it just explodes. The concrete compression explodes and we have a catastrophic failure. Okay. So I don't know, conceptual question. Hopefully on the test, if you get something like that, it's a 30-second thing where you look at it, you read it, and you answer it, and you save time for some of the other harder questions. And maybe if you don't know, you can guess. But hopefully that just talks a little bit about concrete design, because with concrete design, we're always looking for to make use of the compression in the top, right? So we're going to have concrete and compression in the top, and then we're going to have concrete in tension. Concrete. We're gonna have steel in tension on the bottom. Okay, so I should probably draw this so that it's actually uniform here, but we're gonna have this thing. Can I get it? That's a little bit better. We're gonna have a compression block, compression block C, and a tension failure down here, tension. Okay, so we're gonna have compression typically on the top, and then we're gonna have this longitudinal reinforcement on the bottom. And it's interesting, actually, in the reference handbook, there's this whole strain diagram. If you took a concrete design course, your professor probably did something like this, where they show these strain diagrams. They show the compression at the top, the tension at the bottom, and some of these strain diagrams. And here you see tension controlled sections versus compression controlled sections as well. In the code for flexure, you want to have that tension controlled. Okay, so what is C? C is the compressive force in the concrete. So in order for this to have moment capacity, you're going to have some compressive force in the concrete, some tensile force in the steel, and that's going to create a couple. And that couple is going to give you your moment capacity. So if for example, you sum moments about this point C, you'll see that T times a moment arm is going to give us, okay, I'll go back to that. So T times the moment arm of D minus A over 2, we'll get to that, is going to be the moment capacity. Transitionally reinforced is it comes back actually right here. So no, you're fine. I love the questions. The tension controlled section is one where the strain on the bottom, or the steel, is going to strain quite a bit. When you get the moment capacity. When you get a concrete strain of 0.003, you'll notice at the top, these strains of 0.003, they're always 0.003. That's essentially what the concrete code in the United States says failure is for concrete. So the ACI 318 code says when you hit a strain of 0.003 in concrete, the concrete's going to fail. Okay, it's just going to fail. But the steel strain, we're assuming linear strain profile here. The steel strain can be 0.002 or less, and it can be somewhere between 0.002 and 0.005. Typically, steel strain is going to yield around 0.002, and the code says we're just going to go to 0.005 to make sure that it's ductile, to make sure that it's tension controlled, and typically beams are going to fall into this point 0.005. Transitionally reinforced just says it's going to be kind of in between compression controlled and tension controlled. That's it. Typically the code doesn't want you there either. It actually penalizes you with the phi factor. So it's you sort of lose strength if you're in this section. You get your most tension strength, your most moment capacity if you're in this section. So we'll take a look at that as well, but they kind of go hand in hand. But the cool thing is here, when we get to bending, this kind of becomes a little bit of a lookup here. And if we come back here, we get the moment capacity, and we get this basic equation. I say basic. There's two equations going on here. You can go derive this if you want, but on the test you don't want to derive it. You just want to know how to use it. So I'm going to write that equation down. We're going to solve it, and then we're going to send it. So Mn equals As Fy times D minus A over 2. So the cool thing is here, I give you D, right? So you might have to go calculate D, but I give you D equals 17.5 inches. What is that? That's the depth. That's the depth from the top of this section all the way down to the steel, the center of the steel. So the top of the concrete beam all the way down to the center of the steel. Okay, that's D. So we know D. We know Fy, right? We're told Fy is 60,000 psi. So Fy equals 60,000 psi. Okay, AS. What's the AS? The area steel. Well, all that we have here is 4 number 9 bars. So if you don't remember this and you don't have a handy dandy like CRS, actually you won't have this on the test, right? A little cheat sheet that tells you what the rebar ratios are. You can come and you can look this up. So in the reference handbook, there are standard reinforcement bar sizes. So for number 9 bar, the area is going to be 1 square inch. So I use that. Hopefully you can remember that. Number 9 bar, 1 square inch. Okay, so if we come back here, the area steel is just going to be, what do we have? We have 6, times 1 square inch per bar. 6 bars times 1 square inch per bar. That's just going to be 6 square inches. And then A is just another lookup. A is just, there's another formula in the reference handbook here. But if we come back to the reference handbook, we have a formula for A. A is Fy over 0.85 F prime C B. So A is equal to AS Fy over 0.85 F prime C B. So what's this? It's going to be 6 square inches times 60. I'm going to use 60 KSI here. I'm just going to convert kind of on the fly. Divided by 0.85 times F prime C. I think, what did we say? F prime C was 6,000 PSI or 6 KSI. And times B. B is going to be this width. So this is the B of 14 inches. In other words, what this tells us is, this tells us kind of the depth of this block. And it's not exactly the depth of the whole block. It's sort of like a part of a depth. It gives us this. There's a lot more to this, but the long and short of it is it kind of gives you the depth of the equivalent stress block. That's what we'll call it. I mean, it's like if we take a look down here, is it back here? Yeah, so this is, C is the distance to the neutral axis, but A is kind of this distance of an equivalent rectangular stress block. So let's just come back and not worry about that. Let's just chug it out. If we plug it in, crank it out. 6 times 60 divided by 0.85 divided by 6 divided by 14. I get 5.04. Anybody else get something like that? Let me just check my notes here to make sure I did it right. But did I actually calculate it out right? Let's take a look. Yeah, let's look at it. So I think, what I did wrong. Nobody called me on this one. I have 4 number 9 bars here. I don't have 6. So that's the value of having notes and kind of like not trying to completely screw up. Where did I get 6? I don't know. 6 I think is on the next problem. I was already thinking past there. So we have 4 number 9 bars. 4 bars, right? 4 bars times 1 square inch per bar is going to give us 4 square inches, and if we plug that one in, we're going to get a better number here, or a number that's at least correct for this problem. So if I plug that one in, I'm gonna get like 3.36 inches. So now we have everything. So all we have to do is we have to come back and plug in mn equals as, so 4 square inches, times 60 ksi, times d, which is 17.5 inches, minus a over 2, so 3.36 inches over 2. And we're going to get some value here. So 4 times 60 times 17.5 minus 3.36 over 2. And I get about 3,797, which looks absolutely nothing like any of these, right? So this is where somebody's going to throw up their hands and say, I did it wrong. But the answer is no, you didn't do it wrong. What do you notice? Units are a huge thing on the FE. You got to understand units. We have kips and we have inches. Everything's in inches. So what that means is we have units here of kip inches. Okay, so kip inches. So to get to kip feet, we're going to multiply by 1 foot per every 12 inches. And we're going to get, we divide that by 12. We're going to get 316 kip feet. And some of you are thinking, I already spent enough time on this, I'm just going to circle it and be done. But don't do that. That's the wrong answer, because that's mn. It's not phi mn. Okay, so there's going to be some of these questions on there that, oh man, are going to try to mess with you. And they're not trying to mess with you. It's just, do you know it or do you not? So what's phi? If we come back to a moment here, we get phi for tension controlled sections of 0.9. Okay, and if we're compression controlled, we're 0.65, right? That's where the code is saying we want it to be tension controlled, we want it to be ductile, we don't want compression controlled. We're going to penalize you. We're going to give you a low phi factor if you're compression controlled versus tension controlled. So we're going to say phi is 0.9. And somebody out there is going to say, well, how do I know phi is 0.9? You could actually calculate it. So epsilon t equals 0.003 times d minus c over c. And somebody's going to say, what's c? And here's another equation, 0.003 beta 1 d minus a over a. Okay, so we can calculate that out if we really want to. Or we can just say phi mn equals 0.9 times 316 and send this and just try to be happy with it. So times 0.9 is going to be 285 kip feet. And I'm going to circle this one, but I'm also going to show you how to do epsilon t to check to make sure that it's tension controlled. So epsilon t equals what? It equals d minus, let's come back and look at that formula. So if we come back and look at the formula, we get, I'm sorry, 0.003 times, let me just write it the right way. 0.003 times beta 1 d minus a over a. So let me write this the right way. We get 0.003. You kind of get this from similar triangles, but 0.85 d minus a over a. Did I write that one? Normally I do d minus c over c, but here we get beta 1 d minus a over a. So beta, oh, I just wrote in 0.85. It's not 0.85, but it is 0.85. So beta 1, actually it's not 0.85. Let's go beta 1. Are we told what beta 1 is? If not, then beta 1, maybe we're not able to do this. If the code doesn't tell you what beta 1 is, that makes it a little bit more challenging to figure out. So, but the beta 1 does show up in here. Beta 1's a factor that kind of goes from the neutral axis down to an equivalent stress block, and I could probably spend another half an hour on that, and I'm not going to. But basically, this is beta 1's a lookup. We have 6,000 psi, so we're in between 4,000 and 8,000. We're halfway in between. This is a linear interpolation function, halfway between 0.85 and 0.65. It's 0.75. So we're going to come back here, use 0.75 for beta 1, and we're going to say epsilon t equals 0.003 times 0.75 times d, which is 17.5 inches, minus a, which was 3.36 inches. And divide all that by 3.36 inches. Right? Did I do that right? I think so. Let's just double check. Yep. So if we get all that, we can plug that one in. That's a longer equation to plug in. 0.003 times 0.75 times 17.5 minus 6, and divide all that by 3.36, and I get like this equal to 0.009, which is indeed greater than 0.005, so it is tension controlled. And phi does indeed equal 0.9. Honestly, if as long as this reinforcing isn't like excessive, as long as it's like in that, you know, smaller range, you're going to be tension controlled. If you get like multiple layers or huge bars and it's just packed in there, I'd say it's worth, you know, if that's the case, then you might need to look at this section. But for this case, it's not worth it. Honestly, I probably on the test, I would just not do this check. And I hate to say that, but for the test strategy, I'd say probably don't do that check and just assume phi is 0.9. I mean, you can honestly make this question even simpler, and you could say, well, phi mn, you could just estimate it as well and say phi mn equals ASFY times, well, what's this? This is just, I mean, if we look at this, what's that? 17.5 minus 3.36 over 2. This is like what, 15.82? 15.82, which if we look at 15.82 divided by 17.5, 15.8 divided by 17.5, what do we get? We get 0.9. So we could say that phi mn is approximately equal to 0.9d and save ourselves a lot of work. And if I put a phi in here, to actually even makes it better. So we could say this is equal to about 0.9 times what, 4 times, you know, 4 square inches, times our 60 ksi, times our 0.9 times 17.5 inches. I'm going to divide all this by 12 inches per foot. And phi mn is approximately, what's that? 0.9 times 4 times 60 times 0.9 times 17.5 over 12. And I get like 284, you know, kip feet, which is incredibly close for an approximation. But I just did this approximation in about 1 minute, and this one took me about 10 minutes. Okay, and the reason I show the approximation is because it's easier. It's quicker, right? And it gets you into the ballpark here, you know, and if it's close, it gets you into the ballpark, and hopefully you can get an answer. And if you need to do it more fully, you can, but on the FE, some of those time savers are going to be helpful. This equation is not in the reference handbook. That's just an estimation, it's an approximation. But if it helps you, great. If it doesn't, you know, I get that too. Okay, but the real equation's in there, and that's how you do moment capacity of a concrete beam. So what do we do next? We keep going. We got a couple more questions here, and then we'll call it. And here we have a singularly reinforced concrete beam section shown in the figure below. Beam has normal weight concrete with F prime C 6,000 and rebar with Fy 60,000. If this beam must resist an ultimate shear of 25 kips obtained using LRFD design combinations, what statement best describes the shear reinforcement provided, right? So here we have shear reinforcement. Is it required? Is it not required? Is it adequate? Is it not adequate? And this is where we have to go with a couple here as well and figure out how to make it work. So let's go back to shear. So with concrete, we're going to look at moment capacity, we're going to look at shear, and then we're going to look at columns. Those are kind of like the three that I think could show up on the test. So let's go here, shear reinforcement. So with shear reinforcement, we're going to come back and we're going to look down here and we're going to say we have shear strength. So shear strength, again, we have that the strength is greater than the required, right? The provided is greater than the required ultimate load. We have Vn is going to be Vc plus Vs. We have Vc is 2 lambda root F prime C. And then we also come down here and we see Vs. So we have just a whole bunch of formulas. It's just kind of plug and chug. But what we also see is this required word, right? Because this question, the way it's set up is it required? Is it not required? Maybe they would just ask you for the strength, but at least I figured this would get you a couple different things that you'd have to take a look at. One's required, and two is kind of that spacing. Because even if it's not required, sometimes you need just minimum steel in there for spacing and spacing requirements. So let's look at this. We know that we want to see it's VU less than or equal to VPC over 2. So first, let's just go find that V sub C, and then we'll go from there. So what we know is the total shear strength Vn is equal to the concrete strength plus the steel stirrup strength. Okay, so concrete strength plus the steel stirrup strength. So we know V sub C equals what, 2 lambda square root of F prime C BWD. Did I get that right? it's the same formula here. And one of the things that you have to worry about here, and they don't come out and tell you, which is, I don't know, this is one of the things that's tough. There's nothing down here that says F prime C, but F prime C has to be in PSI. So I didn't try and trick you on this problem. I gave you F prime C in PSI, but if they give you F prime C in KSI, you gotta watch out, because that can mess you up. Lambda is just a factor for normal weight versus lightweight. We have normal weight concrete here, so we're good. We're gonna use lambda of 1 times the square root of what? Square root of 6,000 PSI times BW, which is the width, 14 inches, times D, which is 17.5 inches. And we get V sub C equal to 2 times the square root of 6,000 times 14 times 17.5. Okay, and what do we get there? We get about roughly 37.95. I mean, like roughly 38 kips. Okay, if I divide this by 1,000, inch or kips per pound. I'm sorry, 1,000 pounds per kip. 1,000 pounds per kip. Okay, that'll get us 38 kips. Okay, so we have an ultimate, right? We have an ultimate shear of 25. We know that phi VN has to be greater than or equal to VU, and VU equals 25 kips. Okay, so right off the bat, I was saying, okay, well, V sub C is bigger than VU. That's great, but we have to remember, if we come back to the code, and this is actually old code. This is like ACA 318.14, not 318.19. This will probably change at some point too, but what we see here is if VU has to be less than VBC over 2 for no stirrups required. So while we're still here, let's look and find phi. Where's phi? Well, phi's back up here, and we have to look at shear and torsion 0.75. So we come back here, and we're going to calculate VBC over 2, and let's do that. So if we come back, we have to check, is essentially what we're checking is VBC over 2 greater than VU. So VBC was 0.75 times 38 kips over 2, which equals 0.75 times 38 over 2. That's going to equal 14 kips. That is not greater than 25 kips, right? That's not greater than 25 kips. So therefore, stirrups are indeed required. Okay, so what that means is we can cross out A and B. It is required. We know it is required. Okay, so what's next? So is it adequate? Right, so there's a couple of checks that we actually have to do here. We have to make sure that we get our phi VN value greater than 25. So let's check that. Let's go. This was our, we had our concrete portion of the shear strength here. Let's look at the steel portion of the strength here. So V sub S equals, this is where we get our equation again of V sub S is AV FYD over S. So AV FYD over S. And this is where we got to know a couple things. It helps to know the size of these bars. Number 3 stirrups are going to give us a certain area of steel reinforcement. So what we're looking at is we have number 3 bars. These are going to get essentially cut in 2 spots. So we're going to have 2 legs of that stirrup. And let me just write it like this. We're going to say 2 times the area of a number 3 bar. And if we look at the area of a number 3 bar, the area of a number 3 bar is 0.11 square inches. So we're going to say 2 times 0.11 square inches. Oh man, this is, if you haven't taken a concrete design course, I'm just flying. And if you have taken a concrete design course, it's like, okay, I think I'm following along. But like, man, this is where you got to kind of pick and choose what you know, and crush it. And here, so we have 2 times 0.11. We have a 60 KSI strength times D, 17.5 inches. Divided by 12-inch spacing, right? We're told these things are at 12-inch spacing. So we get V sub S. And the number I got there, I believe, is, I should probably just plug it in my calculator to double check. But I got like 19.25 kips. Okay, so we're going to take these two values. We're going to take this 38, we're going to take this 19, we're going to add them together, and we're going to get v sub n, right? So we're going to get v sub n. V sub n equals what? 38 kips plus 19.25 kips. That's going to equal, what's that? 38 plus 19.25 is 57. Let's just say 57 kips, and phi vn equals 0.75 times that, which equals about 43 kips, which is indeed greater than our 25, right? That is bigger than our 25. So therefore that's, therefore that's okay. So the strength is okay in terms of strength. And probably what I should have done in here to limit this question a little bit. I mean, this question is pretty broad. It is adequate in terms of a strength perspective. So I might just add that in here as adequate for strength. And if I didn't, one thing we could check here is we could also check the spacing, because what happens here is in addition to needing stirrups, right, we have a spacing of 12 inches, but there also is a minimum spacing down here where we have required spacings. We have smaller of these values. These are kind of like your minimum steel requirements. So in concrete beams, they want minimum steel in here. And you could go through these, but the 12 inches should be fine for those for sure. And then if we went through this, d over 2, what's d over 2? D over 2 is 17.5 over 2. This is 8.75 inches. So you need the maximum permitted spacing is what? Maximum permitted spacing, let's just look at this for a second. Wait. The maximum permitted spacing is d over 2. So let's just think about that for a second. If this is d over 2, the maximum permitted spacing is, well, let's come back here. So we thought we were all good with this because we have strength, we're okay with strength. But what did we just find out? We just found out the spacing has to be less than d over 2. Oh man, d over 2 is 17.5 inches over 2, which has to equal what? All right, 17.5 over 2 has to be 8.75 inches. So therefore, after all this, we thought we were all in the clear with our strength, right? But it's adequate for strength, but not for spacing. Okay, so I'm gonna go with I'm gonna go with D here, and I might need to update Blackboard, but I'm gonna go with it's not adequate because the spacing is less than what's required for minimum steel. Man, this is one of those questions where, like, if you spend all this time on it, oh man, I'd hate to see them do a trick question like this. I don't think there'd be a trick question like this where it's like it's so involved. But the reason I put this on here was just because it is involved, and I wanted you to see kind of the big picture of the different pieces, right? I wanted you to see concrete strength, steel strength. I wanted you to see the minimums and maximums. I didn't go through all these equations in here, right? All I did was this d over 2, and even over here, if v is greater than phi vc, which it is, vu is greater than no, actually vu is less than phi vc. Was what? Phi vc, did we even get phi vc? No, phi vc, what's phi vc? We can check this, but phi vc is what? 0.75 times 38 kips, and that's like 28.5 kips. So phi vc is indeed greater than vu, which is kind of nice, right? I mean, that's great. But we're in this case here, vu is greater than phi vc. We do see that we have the smaller of d over 2, or 24 inches. So we still have to deal with that d over 2, or in some cases d over 4. But for us, we're going to deal with d over 2, just based on the where we're at with this thing. D over 2 is still that 8.75 inches. And what that does is it limits your shear spacing, so you don't get this shear crack to go in between two stirrups. You don't want a shear crack to develop in between two stirrups. I mean, it's a ton of information. I wish I could teach you a whole concrete design course, but it's, again, this is the 10-minute version, and it's just, a lot packed in there, and that's what we try to do with these sessions, is just pack a lot in there, do a lot, like kind of, is this problem more complicated than what you'd see on the FE? I think so. But could the FE ask you for this VVN value? I think so. Could the FE ask you about stirrup spacing? I think so. Right? It could ask. I don't think it would ask you about all of them in one question, but I think those are the pieces that you have to kind of be aware of. Okay. So a lot going on there. We only have 2 questions left. This one's kind of a quick one, and then the last one is kind of a quick one as well. So hopefully we'll end up. I thought the session was. I always think the sessions are going to go quicker, but then you guys ask questions, and I just get excited and just keep talking about other things that relate. So I hope that helps you, and I hope that it's a good refresher, and it makes it work. So reinforcement ratio for the longitudinal bars in the columns below is most nearly. So this is great. Reinforcement ratio. Okay, we had really hard problems. Let's just come back here. Let's do Control F, reinforcement ratio. And it's working on it. Working on it. And it's working on it. And Acrobat found nothing. So does that mean there's nothing in here? No, it doesn't mean there's nothing in here. It just means you have to look down here a little bit. This is limits for longitudinal reinforcement. It doesn't tell you what rho G is, but rho G is the reinforcement ratio. It's the area of steel over the gross area of the column. So again, this is kind of a conceptual question, but hopefully this is one of those questions that you don't just look it up in the handbook and say, shoot, there's no reinforcement ratio in the handbook. What do I do? But you know that the reinforcement ratio is what rho G equals the area of steel over the gross area, right? Area of steel over gross area. What's the area of steel? Area of steel is, well, we have number 9 bars again, so this is where I got my 6, sorry. So 6 bars times 1 square inch, right? Divided by the gross area. The gross area, we're gonna get 20 by 20, so 20 inches squared. So we're gonna get rho G equal to, what's that, 6 divided by 400 is gonna be 0.015. Which this was, again, sometimes you're gonna have those longer problems and sometimes you're gonna have those like 30-second problems. And if you know what you're looking for, it makes it easier, right? But if you don't know what you're looking for and you're not familiar with some of the terms and you try just to search it in the reference handbook, you're not going to find it, right? So that's where it's helpful to kind of go through some of these pieces. The other thing is rho G here. For columns, typically you want it to be between 1% and 8%, 0.01, 0.08. That's required by the code, and that's where we'll go. Okay. So this one you need to just know it, sort of. You kind of needed to know that this is what a reinforcement ratio is. Yeah, and if you haven't taken concrete design, it's one of those things that at least you took this review course, right? And you went through it. But I mean, I think I talked to somebody recently who took it and said, yeah, he didn't tell me any specifics, but it's like, I kind of like ask in the sense of big picture, like, are there things I'm missing when I'm doing these reviews? What types of topics did you guys see that maybe should be covered more? And reinforcement ratio came up. So we were having a discussion and reinforcement ratio came up. So yeah, that I think that's one of those things where it's like, if you don't know what it is, you don't know how to do that problem. But if you do know what it is, it's like that 30-second question. It's like, bam, I got it. So. But it is in here, right? It is in here. It's just this term doesn't get defined necessarily, so it makes it more challenging. And then we move on to question number 9, and we'll send this one and be done. But here we have axial load-bearing capacity, phi PN. So this is a column. We have a section of it. We're squashing it, and we have a capacity phi PN of concentrically loaded short column FY60, F prime C, 4 KSI. What is it? So we got to pick a number here. And if we come back, actually, we were just there. So we have phi PN, and we got this big, long equation. We can just take that big, long equation and shove it in here. I mean, actually, can I do this? Maybe I can. I don't know. Let me see if I can do this. Let me try to snip this here. And can I get it in? I don't know. Maybe. Oh, there it is. The resolution's terrible. Let me rewrite it here. So I will rewrite it. This phi PN equals 0.8 times phi times 0.85 times F prime C times AG minus AST plus AST FY. Oh man, long equation. It didn't really work when I tried to copy it in, so I won't do that again. But what do we have here? We have some values that we need to go through. So we could look all these up. Phi is going to be 0.65 for compression. F prime C is going to be 4 KSI. AG is going to be 20 inches times 20 inches. That's going to be 400 square inches. AST, that was our steel area. It's going to be at 6 bars times 1 square inch per bar, or 6 square inches. What else do we have? We have, I think that's it. We have FY. So we have FY. FY is going to be 60 KSI. And honestly, this is a plug and chug. So if you are comfortable with plugging and chugging, you plug and chug, and this just spits out a number. And if I did my math right, it spits out a number that is, I think, like 884. If I plug all that in and chug it out, it's going to be 884. So I'm just skipping that step here because hopefully, if you're at this point in your career, you know how to plug and chug like a pro. All right, you got that mastered. So this is a plug and chug. You could plug and chug it, but this is one approach. This is the formula approach. Okay, this is the formula approach. Some of you might have learned this through interaction diagrams. So when I teach a concrete design course, we do interaction diagrams as well. So, and part of the reason we do it is because they show up on the FE. So interaction diagrams, and we can take a look at an interaction diagram here as well. So if we come down to the reference handbook, this is called an interaction diagram for rectangular sections with bars and faces only. You know, gamma 0.8. It is what it is. So this is one, and you'll notice that there's a PN over on this side. We're going to go down to the next version of this, and here you can see we have phi PN over BH. So we have phi PN over BH on one axis. We have phi MN over BH squared on another axis. And these interaction diagrams are used where you have columns and like moment frames where you have to deal with, you know, you might have a value of moment somewhere and a value of axial force. And in a moment frame, you have both, right? Because you have vertical loads and maybe you have earthquake or horizontal or lateral loads that are pushing this thing over, and you got some moments going on in those columns. And the interaction diagram says, well, it's not really moment capacity. It's not really axial capacity. Where does it fit in the big picture of moment versus axial? And this diagram kind of gives you that. But it also gives you phi PN if you really want it. So on the vertical axis, we can solve for phi PN over BH. And I mean, you have to make some assumptions here. But again, if you can kind of get some of those assumptions, we have 4 KSI, 60 KSI, we have gamma of 0.75. Our gamma is not exactly 0.75, but we're close. Phi PN over BH, let's just write that down. So we have this interaction diagram approach. And we can say, well, phi PN over BH equals what? Well, we just did this question before, and we know the reinforcement ratio. Remember that rho value, right? That rho value was 0.015. So we just did this before, and we're kind of in between 2 and 2.5. So we're 1.5 is maybe like 2.2, you know? Let's estimate it at 2.2. So this is going to equal roughly 2.2. So what we can get here is phi PN equal to 2.2. I think I wrote that wrong. It's B times H, not B times N. Maybe I lost my vertical there. B times H. So 2.2 B times H, 2.240. I'm sorry, 400 square inches. And the units are sort of weird here, but what we get is phi PN equals what? 400 times 2.2. 400 times 2.2. Guess what we get? We get 880 tips, which is remarkably close to our 884. Okay, and if for what we're doing here, it's gonna be enough. But I kind of wanted to show you both approaches. I didn't write this whole thing out plugging and chugging. If you want to plug and chug, hopefully it worked. But where did I get this 0.65? Again, that comes from the reference handbook. The reference handbook has those values of phi. So with concrete, there's one section that have all the phi resistance factors up here. So we have tension controlled beams, compression controlled sections, and for columns are compression controlled. So columns are compression controlled. You're going to use this 0.65. 0.65. Uh-oh. You're getting 1223 plugging and chugging. So this is the 0.65. Let me type it out here. Let's go for it. Let's go for it. Let's just try it. I'm gonna write this in. 0.8 times 0.65 times 0.85. There's all these factors, and again, I could go through a lecture on this, but 4 KSI concrete times this gross area 400 minus the steel area of 6 plus the steel area times 60 KSI. I'm getting a little loose on units there, but this is going to be PPN. And if I do this out, what do I get? I get 0.8 times 0.65 times I got to get parentheses here, times 0.85 times 4 times 400 minus 6 plus 6 times 60. And I got in mine 83.792. So I don't know. Check your plugging and chugging. I'm sure it's probably in these parentheses. Honestly, these parentheses are sort of a bear. These brackets are sort of a bear. You gotta get those in. But yeah, the 0.65. There you go. So yeah, the 0.9 bending. And again, this comes from the idea that the code treats ductile failures, that transition or that ductile tension controlled failure, a lot better. You know what? It's not a rookie mistake. This is one of those mistakes I see people make, and like it's 100% confusing. I shouldn't say 100% confusing. It's like, but it is confusing because phi isn't just phi. It's not just the number. It's not just always 0.9. That's where it's like, oh man, there's so many tables, and like you have to know in your mind which table to use, and it can get super confusing. But it doesn't say, this table doesn't say columns, right? It would be nice if it said columns. It's just this compression controlled. So compression controlled is a column. It's a column is you're squashing it, you're putting it in compression, you're trying to close it up, or make it smaller. That's going to be compression controlled. But I'd love it if it said columns, but it doesn't, because columns can actually be in tension, which is another point. But man, there's a lot here. There's a lot in this section, and it's like, again, I mean, this is like we're trying to fit into 2 hours or an hour and a half, 2 semesters worth of stuff, and it's like, oh, how can we hit the fundamentals? But that's where I tried with steel. I tried to hit tension, bending, and columns, right? Compression, bending, tension, compression. With concrete, I tried to hit bending, shear, and columns. Those are going to be your 3 big areas that will probably come out here. So it's a lot. It's 100% a lot, but if you can narrow some of these down, and I talked through a lot of them, so I took a 3-minute question and turned it into a 13-minute question. But it's like, if you can narrow some of these down into 3 to 5 minutes, and maybe get some of these questions that are those 30-second questions that maybe you didn't know before, but now you do know, it's going to help you get more questions. More questions help you to get past. And if nothing else, at least you can stick around for the joke, right? So there's still some people here. And I've been trying to end these with a joke, and there's only so many good jokes. But this one I was happy with, because it comes from, I can't remember the guy that originally said it. He's a comedian, but he probably said it a lot better than me. So this one it talks about okay, so let's just get started. There was a prison bus, and it had an accident. It was transporting prisoners somewhere, and it had an accident with a concrete mixer, right? I mean, the scene was a mess. The problem was some of the prisoners escaped. So the police are on the lookout for 16 hardened criminals. But there was one guy. I think what happened was the guy that was driving the concrete truck, he was plastered. This just gets worse. But there was one guy. He kept saying, "I'm innocent. There must be a mix-up." So there you go. So whatever. That was terrible. But maybe it made somebody laugh. All right. I mean, you need to have a sense of humor on this test. You need to take it lightly, but you also need to study and know your stuff. All right. So I try to end with I tried. I try to end with something light, just to keep it light, and hopefully these sessions do help. Man, I'd like to meet him. But it's fun. Hopefully, you guys will do great, and these sessions help. And you could probably teach me something as well. So, hey, we'll try to do this same time next week as well. And until then, hey guys, keep working hard, keep moving onward and upward, and I'll see you then.